at unfolding Newman projections. Can you do one of those? And sure, let's do one, and let's also assign RNS from that. So we'll kind of do a twofer. So let's say you had a question like this. And the question was, let's say it was a three-parter. Part one, draw this in the most stable Newman projection. Part two, draw this as a line angle formula. And part three, name the compound, including stereochemistry. And so this is the difficulty of naming that you would run into, very not massively complex functional groups, but just really, really basic stuff. And really focusing on RNS. That's where all the real marks are. So part one is draw this in the most Newman projection, stable Newman projection. The first part of that question you should ask yourself is it already in the most stable Newman projection? So I guess, is it in the most stable Newman projection? The lowest energy Newman projection? Yeah, Melitza, we will, yeah. Yeah, okay, thank you, Faith. So no, it's not. So what we need to do is we need to identify the largest groups, the things that should be anti from each other. That should be your first thing. So on both the front and the back carbon, you should identify what you think are going to be the largest groups, so the groups with the biggest A value. One way you can do that is you can look up the A values. The other way you can do that is you can kind of know roughly what you expect to see. And so hopefully using either method, you'll identify that the isopropyl group and this propyl group are your two biggest groups. Isopropyl is obviously bigger than methyl, it's bigger than fluorine. Propyl is bigger than ethyl, not by a lot, but still is. And it's bigger than an individual atom like iodine. So we now need to redraw this. And you can draw, there's a lot of ways you can draw this that would all be correct. What I recommend we do, and I'm just going to do this for the sake of making a point, I do not recommend you actually do what I'm about to do, is I'm going to just rotate the back one. Make sure everything that was clockwise stays clockwise. So going from propyl to iodine is clockwise, it's still clockwise. Do not flip that. Otherwise, if it suddenly becomes anti-clockwise or counterclockwise, you've just switched the enantiomer. And you don't want to do that because the question is about this molecule, not its. Well, I guess you made a diastereomer. You switch that one stereocenter. So the question is about this molecule, not a diastereomer of this molecule. So we have this. This is the most stable Newman projection. The isopropyl and the propyl are anti to each other. I do not recommend that you try and unfold this molecule. You can, you are very welcome to, it is correct. But when we draw a line angle formula, you need to draw the longest carbon chain all in the plane of the page. And that's going to be a little awkward to do when it's not done like that. So what I recommend you do is you take those biggest groups and you stick them anti to each other at the top and bottom of the molecule. Why? Because when you do that, you will naturally get this thing folding into the right line angle formula with the carbon groups in the plane. So you have this. Now, next was a two-parter. It was unfold this and assign RNS. You can assign RNS from here. It's fully possible to do for a Newman projection. You just need to remember the rules that you need to point number 4, the lightest atom, away from you. And so you're going to need to do a little bit of mental gymnastics. Because on the front carbon, for example, the lightest group is this methyl group. because everything else isn't carbon or weighs more. On the back carbon, the lightest group is this ethyl group. And so you'll need to have those pointing away from you. And if you're not really good at three-dimensional rotation, it can be very difficult to do that from a Newman projection. I don't recommend it. If you can see it immediately, go nuts. It's right. You can do it from here, but just make sure you do it right if you do it from here. So instead, what I'm going to do is I'm going to unfold the molecule. Now, what I see is what I first draw is I draw my eye and the carbon chain, just the carbon link between. I'm looking down the Newman projection carbon bond. Why am I drawing it like this? Well, on the side closer to me, the one that is in the plane of the page is going down. If I had drawn it like this, the side closer to me, the one in the plane is going up, and that's not what's happening. It's going down, it's not going up, so I would have to rotate to get this, or flip my head upside down, which would be okay. That's just harder, so I'm not going to do that. So I'm looking down this thing. The isopropyl group is down. In my right hand, I have a methyl group. In my left hand, I have a fluorine. On the back carbon, I have the propyl group going up. In my right hand, I have an iodine. And in my left hand, I have an ethyl group. Anyone having a lot of trouble seeing that, or did I lose somebody somewhere along there? Mouse is about to die. Okay. I'm sorry, Madison. Okay, so maybe I don't have a model kit in front of me, but maybe try and do this with a model kit if you have your model kit. Like actually look at the Newman projection through the model kit. I strongly recommend that if you have trouble with that. Because right, okay, so I'm looking down this bond. I'm going to turn on my camera, so maybe this will help. Probably not, but maybe. Like in a Newman projection, I am looking straight down the bond. So if you imagine your eyes, I'll try and pull out the laser pointer. This bottom piece here is kind of sticking down and kicking you in the nads. Like it's straight down, right in front of you, like pointing straight down, and it's facing right in you. In your left hand, you reach out and you grab the fluorine atom. In your right hand, you reach out and you grab the methyl group. And again, that isopropyl group is pointing straight down into your stomach. Then I turn. I literally just turn to put myself in the plane of the page. And and just because that's the way my eye is, the methyl group is in my right hand, is coming out of the plane, and the fluorine is in my left hand and it's going into the plane because my eye is over here and I'm looking down that bond. Like that's just the way perspective works. How did I get from the first blue molecule to the second blue molecule? I rotated each bond. You can think of it in two ways. You can either think that you rotated the back carbon 60 degrees counterclockwise and the front carbon 60 degrees counterclockwise, or you rotate the entire molecule 60 degrees counterclockwise. Just take if you have this on a screen and it's on a computer screen, that's like a phone, just rotate your entire phone 60 degrees and do the same thing. Like just turn your screen. So on here, you're physically putting yourself in, like, think about grabbing with your hands and, whacking yourself in the forehead or whacking yourself in the stomach with the groups that are coming out. If you If you're having trouble with that, please, please, please build a model. I can't emphasize that enough. I've been saying that now for a week. Yeah, if I'm looking this way, absolutely, right? Like, there's me. I'm like a one-eyed cyclops. Actually, it looks like a mouth, but it's an eye. There's my mouth. This is really looking kind of dystopian. I got hands. So yeah, like, there's my right hand, there's my left hand, right? Like, that's where I am. Why did I rotate it though? Because what I want to do is I want to make sure that the big groups are in the plane of the page, because for this to be right, for me to draw this correctly, this group here and this group here must be in the plane of the page. If they aren't, if you don't have that zigzag going, you haven't drawn a proper line angle formula. How can you tell which one it's the longest one? So just figure out what's your longest chain. The isopropyl group here is longer than methyl, and fluorine is not carbon. And the propyl chain here is longer than ethyl, and iodine is not carbon. So going back to Melitza's question, if you ask you to draw a Newton projection, do you always want to split in the most stable conformation? I always want you to draw the line angle formula, which might not be the most stable conformation. If I ask you for the most, I asked you here for 3 different things: most stable Newton projection, line angle formula. Those might not be the same thing. You might need to rotate the Newton projection to get the most stable formula, or the line angle formula. Yeah. But basically we're looking straight down this bond. There's like, there's like a balloon in between. That's what this circle is. And then we can see the front carbon. We can't see the back. All we can see is stuff sticking out from it. Yeah, okay, that's a good point, Melissa. I will do an example like that. I just said. We'll do a couple more of these. Okay, so now we've drawn this thing out. This is in our longest chain is in the plane. We checked that. So we've drawn the right line angle structure formula. Now we need to assign R and S. And so what we quickly want to do is assign priority on this carbon. I'm just going to label A, B, C, and D. I'll erase these in a moment. Quickly, assign those priority 1 through 4. Just practice. So Leon asked, would it be wrong in the exam if we don't draw the longest chain in the same plane as a page? It would be slightly wrong. You would probably lose like a quarter mark. It's wrong, but it's not. As my wife says, it's wrong that tomato is a vegetable, but it's very wrong to put tomato into a fruit salad. So it's the slight wrong. Chitra, yeah, that's a fair question. I can ask you guys to do some double Newmans and take the 6-membered chair and turn to a double Newman or backwards. Okay, so if you've assigned priority, which one's number 1? A, B, C, or D? Which one's the highest priority? Okay, we got C as the highest priority. Awesome, right? It's the heaviest atom. It's not carbon. Everything else is a carbon. So don't remember, it's not the weight of the entire chain. It's just the next atom. Perfect. Alan, I will. I'm not sure what the fail-safe method is. But I can show you how you can determine that is a chiral. There is no fail-safe method. Okay, what's number 2? What's your second highest priority group? Not always, Melissa. I'll show an example which is not, which is what you asked, I think. D is the second highest. I completely agree. You guys are all awesome. So you have a carbon that's attached to an iodine. All the other carbons are not attached to iodine, so they're going to lose. And then I don't need to ask for this audience because those of you who answer the questions will get that right, and those of you who don't answer aren't going to answer in the chat. So this is our priority. Now, we've ranked the priority, and we note that 4 is coming out of the plane towards us. We need 4 to be going back into the plane away from us to assign R and S. Right? That's necessary. We can cheat by just remembering that 4 is coming out of the plane towards us. We do the rotation. It looks like an R, it looks clockwise, but 4 is coming towards us, so it has to be the opposite. So this is S. If I lost you there, you can do a couple of things. You can physically switch the methyl group and the fluorine using the trick. It's one switch. Now 4 is backing away from you. And it will look like R, but you made a switch, so it has to be S. Or you can rotate the entire molecule in your mind to have 4 pointing back and away from you. And it will look like S. Why is it only one switch? Because all you need to do is switch 1 and 4, and now 4 is backing away from you. So you only need to do 1. You're only switching 2. You're doing 1. You're swapping places only once. Yes, to assign R and S, 4 must be in the back. If 4 is not in the back, you cannot assign R and S. If 4 is coming towards you, you cannot assign R and S. If 4 is in the plane, you cannot assign R and S. 4 must be going away from you. Must. Okay, so that's S. If we look at this other carbon, I think we can assign the priority pretty quickly. I'll do it in red. The iodine is going to be 1. This is going to be 2. This is going to be 3. This is going to be 4. I don't think anyone would have anyone who didn't have difficulty with the last one is not going to have any difficulty with this one for the same, it's exactly the same logic. In this case, we note that 4 is going back and away from us. Great. We don't need to do any kind of rotations. We just go 1, 2, 3. It's R. We're good. So now we need to name, if I ask you to name the molecule, you need to figure out what or where to start your chain name. Whenever you're naming, you need to start, where does your chain naming begin? You want to name the longest chain. I think I said I wasn't going to ask you to name compound, so I'd probably just ask you to assign the stereochemistry to a center for the midterm. For the final, naming is valid for things like this, but I did say I wasn't going to ask you a name, so I'm not going to ask you a name. But I would ask you to, which would probably be easy marks, but I said I wasn't going to do it. So you would start here because you'll start with a 1 over on the left-hand side because it will minimize your numbers. I'm not going to cover naming this. You can practice naming it. What I would as a structure on how to go about doing that, I would make sure you write all the pieces down and then slap the name together. Don't try and write the name at once. Just make sure you note that there is a 2-methyl, there is a 4-methyl, there is a 3-methyl, a 4-ethyl, a 3-fluoro, a 4-iodo, and it's a heptane. So just make sure you have all those components together and then start ordering them. Almost like they're on flashcards. You can just move those sections around. Okay, I'm going to go with No, Fatima, you don't need to withdraw. You don't need to redraw it if you don't want to. If you assign RNS correctly, you get the mark. I'm not. I'm asking you, is it RRS? I'm not asking you that there has to be a specific way that you have to determine that. Whatever way you use to determine it and works for you is the one you should use. There's no right way to do it. Just 4 needs to be in the back. However you get 4 into the back is up to you. That's between you and your chemistry fairies. So let's have an example where the anti is not the most stable chain or the longest chain. There's some really into fluorine today. So we have an example like this. I have drawn this properly for the Newman projection. This is the lowest energy Newman projection. The groups with the biggest A values are the 2 isopropyl groups. I have my biggest groups anti to each other. The groups that are going to take up the most space, the most sterically hindered ones, the ones with the biggest A values, however you want to think about that. I do not have my 2 longest chains anti to each other. So to do that, I am going to need to rotate, and what I'm going to do is I'm going to rotate front carbon to unfold this properly. 60 degrees clockwise. So if I do that, no, that's not what I want to do. I want to rotate my 120 degrees anti-clockwise. I don't know what I was thinking. And not Celsius. You don't need to write this. I'm just writing this so that if you look at the notes, what the hell did you just do? If you can read my scribbles. So 1, 2, 3, 4, 5. So I have redrawn a Newman projection. This is not the lowest energy Newman projection, but this is the Newman projection we need to unfold to get the right line angle formula because we need the longest chain in the plane. How will we know the long right chain does not have a bigger A value if you ask us to draw in a more stable conformation? You have tables of A values you can look up, but basically A value, what an A value does and what steric bulk is all about is how does the stuff that is close to me bother me? Yes, there is a lot of stuff attached out here, but functionally, this chain is no real different than if it was just an ethyl group. Because all I really care about is what is going on with this carbon. This is only monosubstitute, it's only got a single carbon, it's not taking up that much space. This is, it's got 2 carbons, it's taking up more space. The A value is going to be bigger. You will always have tables of A values. Even if this was an in-person exam, I would give you tables of A values. So it's, I think they're on the midterms, the practice midterms and the final quite a bit. I think there's tables of A values. So you always will have tables of A values you can check these things from. But you also get a sense that it's bulk right nearby, like it's stuff right adjacent to the area you're talking about. You don't really care what the hell is going on a distance away. It doesn't matter. It's what's going on right here, right now, because what we're trying to do is stop things banging into each other through this bond. And all that matters is what's right around that bond. So we rotate it, we get like this. This is not, the second one I've drawn here is not the most stable Newman, but it's the thing I need to do to unfold it. I could have unfolded from the first one, I would then have to rotate it once I unfolded it. And in a lot of ways it's easier, I find it easier to rotate a Newman projection. If you find it easier to rotate a line stick formula, go nuts. Either, it doesn't matter, either works. So again, In this case, now notice that my front carbon is whacking me in the forehead instead of whacking me in the nads. And so I'm going to draw the bond between the two carbons like that. So that the front carbon, the big pentyl chain, is going straight up. In my right hand, I have fluorine. In my left hand, I have isopropyl. On the back carbon, I have the isopropyl group. And in my right hand, I have fluorine. And in my left hand, I have hydrogen. And then quickly go and assign priority. Note that although this carbon chain is longer, you break the tie at the first carbon, right? Because this carbon, the one priority 3 has 2 carbons attached to that carbon, whereas 4 has, you start hitting hydrogens. Can you assign, so it says anti-clockwise. Or counterclockwise. I guess how normal people say it. Can you number the Newman? Yeah, you can if you like. It's hard to get the number 4 priority set up properly. How do I know how long the chain is? Because it's there. 1, 2, 3, 4, 5 carbons. There's 5 carbons on there, so 1, 2, 3, 4, 5. That's longer than the isopropyl is just 2. And the longest chain on the other side is just this 2, the isopropyl. I think I'm not answering your question, Mohammed, and I don't quite understand. I'm confusing you somehow, and I don't know how I'm confusing you. That's not on you, that's on me. There's something not clicking. Yeah, you can, yes, yeah, you can draw a zigzag any freaking way you like. Yeah, that's absolutely. Actually, you are more right than I am, Melitza. So, 1, 2, 3. That's better. Mine was okay, you get the marks, but this is better. It's kind of all in a plane. It's all straight. In the first one, the smallest group is not going into the plane. Here, like up here, you mean? This is number 4. Yeah, so we have a problem here because now number 4 is in the plane. If it's coming straight out towards you or straight back, you can do a quick mental chip. If it's in the plane, there is no way to cheat. You can do 2 things. One is you can quickly realize that you got 2 options basically. You can either pretend you're looking down this bond, like straight onto it, in which case you're kind of making a new Newman in your mind. If the thought of that makes your skin crawl, quickly switch number 3 and 4 and just do that switch. So in which case what you would do is you would redraw this. Just the center. You don't need to draw the rest of the molecule because all that matters is the priority here, right? All we're trying to do is assign RNS. So I would just quickly sort of sketch out this. I wouldn't even write, I would just write the numbers. 1, I switched 3 and 4. Sorry, the 1 is kind of fading into the blue of the U Windsor template. Make it orange, stand out better. And now I can take a look at that and go, yeah, that looks like S, but I made a switch. So the original one must have been R. You could have equivalently have sort of positioned yourself staring down at this thing and gone, yeah, that's an R because I'm going clockwise around it when 4 is sticking straight back out away from me. It all depends on how comfortable you are rotating and moving things around from 2D paper into 3D. If you're still lost at this and you haven't gotten out your model kit and you haven't spent like 4 or 5 hours with your model kit going through the examples we've gone through in class, I've got zero sympathy for you. If you have spent 4 or 5 hours with your model kit going through the examples we've gone in class and the examples on the assignments, and you're still having trouble, keep at it. It will click eventually, I promise. Even for those of us who are the least three-dimensionally oriented. I don't know my left from right, and I get really confused about clockwise and counterclockwise, and I'm a shitty driver because I can't find my way around anything, and you do not want to see my attempts at sculpture or architecture. Luckily, no one's let me build anything. I tried a shed once. It fell over. So I am not good at this. Three-dimensional thinking is not something I am natural at, but it does come, and it doesn't come in like 15 years. It comes in a few weeks of doing this pretty steadily. It's R. So it's R. R is the answer. This is a flip. This is a rotation. All I did was this was a convenience for me to figure out whether that was R or S. So the blue one's R. The red one is obviously S. Because it's counterclockwise. 4 is going away from me. That one's freaking simple. So you would label those as R and S, and that would be your answer, and that would be right. How could I tell this one was R? I can flip it in my mind and stare straight on down this bond so that this is pointing directly away from me because I am down here looking at it. I'm sorry. Yeah, you can swap any two groups. That the swapping of groups, if that's your question, Melissa, you can swap any two groups anywhere you like on that thing. Can we do more of these? Yeah, it covers the scope of what we're doing. Today we're talking about R and S and naming shit. So yeah, of course we can do more of these. Yeah, okay, so let's go. Which part are you more lost at, Madison? The Newman projection unfolding or the assigning R and S side? And we have a hand up. Alyssa.
Hi. Do you mind just going back to the last page? So
That one?
Yeah, the bottom right example. I'm just confused because you see where like the first one is for the first Newman projection, or sorry, the first R, where R is.
Sorry, I thought I switched on my laser pointer. I didn't. Okay, so for this R here, this one?
Yeah, so you see where
Okay.
1 is?
It's the fluorine, yep.
Right. So how would you know if you'd go to the right or the left? Like, are you going towards 2?
Yes, so what I'm doing, if I'm rotating this in my mind, is what you're saying, right?
Right.
Okay, so my eye is down here, so I go 1, 2, 3. So if you can imagine what you're doing here, what I'm thinking is my eye is down here. So I've got this chain here sticking me in the forehead, going straight up. If my eye's here, right?
Mm-hmm.
I've got fluorine in my left hand. I've got isopropyl in my right hand. And I've got this pentyl chain pointing directly back away from me into the screen. And so if the fluorine is 1 and my forehead is 2, I go from left, and I'm sorry, my camera's inverted, I think. But if I go from left to the top of my head, and that's going clockwise.
Okay.
So that's R. Did that make sense?
Yeah.
Cool. Okay. Use the hand raising thing too if you need to interrupt me and you want an explanation on that, just like Alyssa just did there. That's the whole point of this flipped class. I'm going to look back at what Madison answered. Oh, she didn't. Can we go? Yeah. Unfolding is where I'm getting confused. Okay. So let's unfold stuff. Okay, apparently I am just. There we go. So let's draw Newman. Let's keep it a little bit simpler. I promise this is simpler. It just gives us lots of labels. So everything's the same. There's not a lot to grab onto. In this case, it's not clear what the longest carbon chain would be because there's no freaking carbons attached to the front one. So it doesn't matter how I unfold it. It's entirely up to us. Yes, when you unfold, it's the line angle formula. Yeah. If possible, can you show us using your model? Yes. Now I put all my model kit away somewhere, and I don't know where. Like, my office is a disaster zone, and there's really not many places I can hide stuff. Found it. I need to invest in one of these oversized novelty model kits. Okay, I'm going to actually do a much simpler example just because the way that colors work on models. You know what, actually, maybe I can do this. I'm just going to change it a bit. So I'm just with those rules so that we're all on the same page. I apologize, this will take me a moment to build the model. You like some, you know, Jeopardy music. Okay, I'm going to face this towards you. It is a Newman projection. If we assume that the iodine is blue, I should really check to see what my camera looks like. There we go. I'm having trouble telling if I am showing you the enantiomer or not because I'm having trouble figuring out what you're actually seeing on your camera. I think you're seeing the opposite. I think I need to make the enantiomer of this. Okay. Or I could learn how to invert my camera, but that sounds like work. Okay, so what you're staring at here is this is what I have on the page. I think this is exactly what I'm seeing on my screen, right? The iodine, like a Newman projection is we're looking straight down this carbon-carbon bond. This iodine, this blue atom is whacking you in the forehead. You can grab this guy with your left hand, this fluorine. You can grab this hydrogen with your right hand. On the back carbon, you grab the hydrogen with your right hand, fluorine with your left hand, and this methyl group is pointing down. I think it was right before too. No, it doesn't matter, Victoria, but I think, okay, so you're seeing the inversion of this. You're not seeing this. Do you want me to flip it? Yeah, I can flip it. Yeah, I think so too. Okay. So when we're unfolding, what we're doing is we're moving this bond from looking straight on to looking at an angle. And normally what we want is we want the longest carbon chain in the plane, so we can do it like that. So all the atoms are like that. So again, what we've done is we've gone from looking at it like this to looking at it like that. Like this to like that. And so when I see it like this, I'm gonna put it like this, sorry for now, because, and my eye, I was looking at it like that, and now like that. So what we're doing when we're unfolding is you're shifting your eye from looking straight on to looking down from this angle down here. This is where my eye is down here, where my hand is, and we are looking at it. So we were doing that, and now we're doing that. Absolutely right, Guntas. Okay, so what? Gosh, I'm hoping I draw this. So if I'm looking straight down, my fluorine should be in my left hand. Okay, so I guess I'm looking at it like this. So if you're all turning your eyes around, seeing it the way I'm seeing it, then we're good. So the fluorine is in my left hand, right here. So if my eye's down here, fluorine's in my left hand, hydrogen's in my right. On the back carbon, fluorine's in my left hand, hydrogen's in my right, and methyl is down. So what I've done is gone looking like this to like that. I don't love doing it with the camera because, again, we're not quite on. The camera's kind of inverted, and my angle is in from your angle, and some of you might be thinking about where I'm looking at it versus where the camera eye is looking at it. And right now it's set to be right from where I'm looking at it. But what we've done basically is you're looking straight down this bond, and you flip from looking straight on to moving your eye down to this angle. And now you're drawing what you see from like a fake eye that's coming straight on where our camera is. And I'm not sure how else to explain that. I might leave it for Samra to try and take another tackle on this. Some chains are longer than 3 carbons. How do we know how many carbons there are behind? There's always only a single carbon, like a Newman projection is always only looking down 1 carbon bond. So there's only ever 2 carbons. You sent those by email, right, Melissa? Oh, in chat. How do you want to resend them? There's been a lot of chat. Oh, between dias. Oh, yeah, okay. So there was actually a question that Alan posted, and I think we lost him. And Alan was saying, okay, without like playing with planes of symmetry, how can I tell if this molecule here is achiral? Well, let's say you're asked, is a molecule achiral or something? First thing you should do is draw the mirror image of the molecule. Always. You're not looking for a plane of symmetry within the molecule, you're drawing the mirror image of the molecule. And if you're a neater drawer than me, your mirror image probably looks even better than mine does. Mine looks like, you know, it's Halloween. It's like a spooky Beetlejuice kind of mirror image. And what we need to do now is, can I superimpose the mirror image onto the original structure? That's the question. Because if I can, then the molecule is meso, and it is achiral. And I clearly can. I can do it by rotating the molecule around like this by about 180 degrees. If I do that, 180 degree rotation of this molecule, we're keeping track of all the atoms. It's the same as that molecule. Same thing. Compound is meso because it has stereocenters. There's no question these are stereocenters. They're attached to 4 different atoms, 4 different things. It's just the molecule has stereocenters and is achiral, and so it is a meso compound. A compound that is achiral but does not have any stereocenters is not meso, because it doesn't have any stereocenters. This one does. Yes. Yeah, so Aurora and Melitza had exactly the right answer there. That is the freaking dictionary definition. Okay, so let's say we have a different system. I can make this more complicated, but in the end, they all come out to the same thing. So I've drawn 2 molecules there. And I can ask, what is the relationship between these molecules? Now, there's only one stereocenter, so they can't be diastereomers, because you need more than one stereocenter to be diastereomers. So if there's only one stereocenter, there's only 2 answers. They're either the same compound, or they're enantiomers of one another. Yeah, so Drake, exactly. So if you, going back to the previous question. So if we can rotate to make it able to be superimposable, that is achiral. Yes. If a mirror image of a molecule is superimposable on it, it's the same molecule. And so the molecule doesn't have a non-superimposable mirror image, and you must have a non-superimposable mirror image to be chiral. Like, this blue sphere is a sphere. Its mirror image is another blue sphere. They are superimposable. They're, like, I can't physically get them into the same space, but that's because I'm working with real items. These are not chiral because their mirror images are superimposable. You must have a non-superimposable mirror image to be chiral. Well, this molecule is chiral. It's just, is it? Yeah, this molecule is achiral up here. Yes, this guy is chiral. It's just, are these enantiomers or not? So what we need to do is we need to fix this so that we can actually compare. Because right now the bonds are going off in every which direction. I can't actually compare them because, well, that's in the plane. That's in the plane. Those aren't I can't easily superimpose them. So what I have to do here is I'm going to have to rotate one of these to fix this. And you can do this any way you want. Personally, I think it's easiest if I hold this bond steady and I kind of spin the atom like a top. So if my camera's still on, yes. So I just hold this one of these carbons steady and I just spin the other guys. Because then I just rotate everything. That's easiest. Instead of trying to rotate the whole thing, which gets confusing. On paper, it's easy to hold one thing steady and then just rotate everything else. So that's what I'm going to do. I'm going to hold, I don't actually know what the answer to this question is. I'm going to hold this one steady and rotate everything else so that I get things in the same shape. It's not much of a rotation. But it's a bit. So the methyl group moves back into the plane, the iodine stays back, and the chlorine moves out of the plane towards me and off the plane. Okay, this and this, the methyl group's in the same place, but nothing else is. So you can do what you want with this. You can either try and rotate, or you can start switching groups. If we want to rotate, we can play the same trick. We can hold this group constant and go, you know what, I'm going to try and move the iodine up to where the chlorine is. So if everything moves 120 degrees, the methyl group hasn't moved, same place, I'm using that as my axis for spinning. My iodine is now coming out towards me. So it's moved to where the chlorine is. So I've rotated counterclockwise. The chlorine has moved to where the fluorine was, and the fluorine has moved to where the iodine was. And now I can see that these two things are the same thing. So these two molecules are the same thing. So these are not enantiomers. Let's say we had a different question. So I guess the question could be, what is the relationship between these two molecules? Are they diastereomers? Are they the same compound? Are they enantiomers? There are two chiral centers. We need to do a quick check to make sure that they are still constitutional isomers. Everything is attached to the same thing, and yes, it is. This carbon is attached to a chlorine and a fluorine, a methyl, and then the rest of the thing. This one is attached to a fluorine, an iodine, a methyl, and the rest of the thing, and so that works. They are the same connectivity. So they can be diastereomers and enantiomers, or the same molecule. If they didn't have that, they couldn't be any of those things. They wouldn't be isomers. So, problem is, stuff's not rotated right. So again, I'm going to do the same trick on this guy to try and rotate this back carbon. So it looks the same as the front carbon, like as the left-hand structure. Notice I'm only working with one. I'm leaving the other one static. I think I recommend this. You're going to get yourself less confused this way. So all I've done is I've tried to get my plane looking the same as my other plane, my first step. And I think we kind of answer our question here, because what we can look at is two of the, like on both these carbons, two of the atoms are in the right spot because we've drawn the plane properly. Sorry. No, it's not necessarily the case. What we should probably do on his back one now, and on his front one, that's fine. On his back one, we can't really tell what the hell is going. Oh, sorry, the fluorine is in the same spot. The fluorine and the methyl are on the same as they are here. And so in this case, for this back carbon, this left carbon, the fluorine and this thing are in the same place, but the iodine and the methyl group have switched places. So these two stereocenters are not the same. Because to make them the same, I need to do one switch. I need to switch the iodine for the methyl. And if I switch the iodine for the methyl here, I would get that guy. So that stereocenter has been flipped. It is the opposite version of that stereocenter. And we have the same thing happening on this stereocenter. These are also not the same. It's been flipped. So the molecule has two stereocenters. I have flipped both stereocenters. What are these molecules? I think we have all possible answers in the first three responses. I am Melissa sitting on the fence, going it's either the same or the enantiomer. But if they're the same, I wouldn't have flipped any stereocenters. Jesse has diastereomers, which means I flip more than one, but not all the centers. And Alyssa's with enantiomers, which is I flip all the centers. There are two centers, I flipped two centers, I flipped all the centers. These are enantiomers. Okay, another way is, let's say I don't understand what just happened. I don't like this rotation thingy, it upsets me. Another option you have is you can assign R and S to all those centers. And if you'll do that, you'll get the same answer. All your R's became S's, all your S's become R's. So you have a choice. You can rotate the molecules or you can assign R and S. Neither one is better than the other. I think rotation is faster. But neither one is wrong. They're both good ways to check to see if these are enantiomers or diastereomers. Yeah, I can show that method. So let's start with this one. I'm just going to redraw it. And we're not going to rotate anything. So for that carbon, we do priority. That's how we do it. Now, if you are one of the people who doesn't want to rotate anything, you're not going to want to rotate anything. So let's just switch 1 and 4. In that case, this would be 1. This would be 4. 4 is now going, and I switched to 4. I didn't care about 1. I wanted 4 back and away from me. That's all I cared about. I switched whatever I needed to get 4 back and away. Now I go from 1 to 2 to 3. 4 is back and away. That looks R, but I did a switch. So it's S. And now I'm going to do the same thing here. I'm going to switch 1 and 4 again because I want 4 back and away. And I go from 1 to 2 to 3. It looks S, but I did a switch. So it's R. So Melissa asked, I thought you could have mirror images where all the centers flip, but it could still be achiral. It's possible. That was actually this example here. Both of these centers flipped. The molecule is still achiral because it's a superimposable mirror image. To be achiral, a molecule must be superimposable. Its mirror image must be superimposable. By definition, if you have no chirality, you have no mirror image. If you have a mirror image that is non-superimposable, you are chiral. If you have a mirror image that's superimposable, so your mirror image is yourself, you are achiral. In this case, it is a mirror image. By definition, the center is flipped. But what I did was I superimpose, if I number this 1 and 2, 1 and 2, I've just changed my numbering, I'm sorry. Then this is 1 and 2. And so what I've done is I've flipped 1 and 2. They're the mirror images. And for this to be achiral, though, 1 maps onto 2, 2 maps onto 1. Because 2 and 1 and 1 and 2 are very closely related. There's a very high symmetry relationship between 1 and 2. Because there's an internal mirror plane. I flipped all the stereocenters. There were 2 of them. The molecule is still achiral because its mirror image is superimposable. That's not the case here, because there's no internal mirror plane. There can't be. The things are different. There's a chlorine and an iodine. If I had had an iodine at both these things, and 2 fluorines and 2 methyl groups, we would possibly have internal mirror planes, and we might have that same situation. Okay, so we have S and R. If I now look at this molecule, and I'm going to draw it big, down here. Just do my priority thing. Again, we're not into rotating things because rotating is for chumps. So I am just going to move 4 there and 2 here. I'm moving 4 back and away from me. Again, I swapped with whatever I needed to get 4 back and away. Then I go from 1 to 2 to 3. That is going counterclockwise, but I made a switch. So it looked S, but it's R. And this guy here, I do the same thing. I want 4 back and away. So I swap 4 with 1. And then I go 1, 2, 3. That looks R, but I made a swap, so it was S. Then I compare these ones. The left one was R, it is now S. The right one was S, it is now R. I have flipped all the stereocenters. I have enantiomers. So whether you do this by trying to rotate these and try and see if things match up and line up, or and go like, no, those are mirror images of each other, or if you assign R and S, you get the same answer. You always get the same answer. It's kind of like, you know, for almost any math problem, there's a geometric solution and an algebraic solution. They give you the same answer. They're just 2 different methods. These are 2 different methods, whether you're using sort of the assign R and S or looking, which is kind of like the algebraic kind of thing. It's using sort of the logical math thing, or you're rotating things, which is literally geometric. Both of them are completely valid. They're 2 roots to the same thing. The assigning R and S is kind of an abstraction of three-dimensional rotation. They're the same thing. So how come having these? We can try. You can try and superimpose these. The thing was they were superimposable. Here they're not. This previous example, they were non-superimposable. It was achiral because the two centers are kind of attached to all the same things. So as I said, I had to put center 1 to, when I did the mirror image and I superimposed them, carbon 2 superimposed on carbon 1, carbon 1 superimposed on carbon 2. Whereas here, carbon 1 is attached to a chlorine, carbon 2 is attached to an iodine. Good luck superimposing an iodine on a chlorine. You can't do it. They're different. Like, they're not, there's no internal mirror plane. Did that make sense? Like, if this carbon had been attached to an iodine instead of a chlorine, then I'd have to consider that. But this carbon and that carbon are not the same thing. In the previous case, they were. Sorry. I can argue, and so I think for a molecule to be achiral, the stereocenters must all be attached to the same things. So here, both stereocenters are attached to an OH, an H, part of the cyclopentane ring, and the other carbon with the OH, the H, and part of the cyclopentane ring. Like, the two centers are the same. And so when I take the mirror image, I'm not putting this carbon back on, I'm not superimposing this carbon back on itself. Like, there it is there. I can't superimpose this carbon back on that one. I can't. But I can superimpose this carbon on this one. But that only works if this carbon and that carbon are attached to exactly the same things and are kind of mirror images of each other. Because if they're not mirror images, if they're not, like, there's no mirror plane, if they're not the same thing, then I can't superimpose this on this in the mirror image. Yes, you know this is, yeah, Alan asked me to tell him why, can you not use symmetry to explain why this is achiral. But yes, you can tell this is achiral because there is a mirror plane right down the middle of the molecule. Yes, there has to be a plane of symmetry, Alyssa. Sometimes those are easier to see than other times. And I guess an example of that when it's not easy to see is this molecule, for example. Like, this is purely, this ring here is perpendicular to this ring here. So there is a mirror plane straight down the middle there, where this is kind of bisecting all of these atoms, this mirror plane. Melissa, I agree. You're right. It doesn't. Yeah, flipping all the stereocenters doesn't tell you whether you've made the enantiomer or if it's the same molecule. You're right. You need to then see if you can superimpose it or not. Because if you flip all the mirror, so Melissa was saying in the chat, her issue is when we have stereocenters and they've all flipped. That doesn't tell me if it's achiral or if it's you've made the enantiomer. And that's absolutely true. If you can superimpose them, it's achiral. If you can superimpose the mirror image on the original molecule, it's achiral. If you can't, they're enantiomers. Okay, so we're 25 minutes over. I'm going to leave this here. again, this portion of the course because the two stereocenters were not the same. So it's for this to be possibly achiral, this stereocenter would need to be attached. I'm going to go with my laser pointer. This stereocenter here would need to be attached to all the same things as this stereocenter here, because I would need to be able to superimpose the mirror image of this stereocenter onto that center. And I can't do that because this one has a iodine on it, this one has a chlorine on it, and iodine and chlorine are not the same thing. They would need, if this was a chlorine, then I'd have to be looking at that because it would all be the same thing. But if these two stereocenters are not attached to all the same things, it can't be achiral. I'm going to leave it to Samara to see if she has a better definition, because I don't think I am going to. I can't do this. This is a failure on my part. I can't see this the way you have. Samara might have a different way of describing it. I also recommend playing around with your model kit and taking a look at Khan Academy or something like this. I strongly recommend using any of these tools. That's the whole point. But again, if you're having trouble with any of this stuff, please, for the love of all that is holy, become familiar with your model kit. It's your best friend. I didn't ask you to buy it because I want you to spend money with some faceless corporation. I get no kickbacks on model kit sales. Though I probably should arrange something. But it's because it's the most useful tool. If you have trouble rotating stuff, the model kit does the rotation for you. You can actually see things. So you can make two versions of something and play around with it. I can't recommend it strongly enough if you haven't done it. Perfect. Thanks, Leon. I'm going to leave it here. I'm going to hand this over to Samara. I'm going to stop recording and take off so she can handle it from here. Thanks, Samara.